I'll be talking a bit today about what type of problems we're interested in Shutterstock and how deep learning has affected the way we approach them. We've been in business 15 years. We work around the world. We help people find better imagery for their websites, for their advertising. Worked with a lot of third parties doing that, but also directly. Like recently, I looked at a map that we showed download activity for the last less than a week around the world. You couldn't find a country on there we weren't getting downloads from, other than like all of Africa. There was one country, Southern Sudan. They probably have no internet. Falkland Islands, Greenland, there was downloads across the board. So we support a lot of languages, and there's different taste into what people actually like. So what type of problems do we deal with? We're dealing with helping people find the right images at the right moment. We have an architecture to handle that. I'll talk a bit about that briefly. Then really get into why data science matters and how we use it a bit briefly. And then get into examples of products. We're going to discuss 4 different products that we have in these areas that use deep learning and how we use it and what type of results we get. The basic problem we're dealing with on image search, and there's some thumbnails, is on a typical screen when a person types a keyword, we show them 100 images. And that's quite a few to pick from. Then they tell us with further keyword searching, or they pick an image and they click on it and say, I want more like that, similar images. We have to come up with the right combination of images for them to select from. Some users are very focused. They know they're doing an ad for a Group M, for an agency. They're doing some sort of Chrysler ad, maybe. Other people, not sure what they want. Maybe they're creating a new website. Not sure what themes to use. Very broad audiences. We sell many things. We sell imagery. We sell video footage. We sell music. We actually have original music. And we have contributor. All these things are from contributors mostly, vast majority. And we sell editorial tools, services to make all these things better. We help people, both small, single individual users, SMBs, and large corporations, everything in between, around the world. Where does deep learning plug into this? It plugs in quite a few places, actually. And, the first place that you see it is, I'm not sure how this works. That doesn't matter. Ingestion. So we get contributors upload imagery. They try to make some guesses as to what keywords to put with it. Crowdsourcing type taggage. We give them some help. We then review it, possibly, and it enters the system. Certainly that's an area where deep learning can help out a lot. Detecting what are the right tags, complementing their tag choices, reviewing the content that comes in, grouping it. But the real area we spend most of our time is discovery and exploring. Discovery we really look at as you're not sure what you want. You're just searching around for things. And exploring is more you're on a focused path. Either way, you want to find solutions that make sense. And so those are 2 main areas, both ingestion, review, and then of course discovery, exploring, where we help out people a lot. The problem is, here's an example of a tag set we get on one of our imagery. This is real. I checked it even before this briefing. You just type that SKU number, that ID number in our window for the search item, and it'll come right up. And you see in red some very interesting terms. You could debate whether you agree that they're all horrible. Vehicle, you might argue, is semi-correct. My favorite word up there is white. I think that's an excellent choice. And so always the test that you try to give it is, if you typed that word and this image appeared, would you want it? And I think you can see here, these are all one-word keywords. I'm pretty sure I'm correct on that. Unigrams. They're very vague, for the most part. They're not great choices. Other problem that you have with words, keywords, is that they don't necessarily mean one thing. Jaguar can mean an animal in South America. It can also mean a car. Now made in India, I believe, or owned by an Indian company. We have lots of traffic on our site. We're number 1 on our space. 51% of the people that search on stock image or something like that come to our site first. But this also means there's a lot of work to be done. Typical image archives, we have hundreds of millions of images, whether it's Flickr, whether it's us, whether it's somebody else. Typical image collections that are being used by people for these purposes might see 20% to approaching 30% ever get used. The rest never gets seen. Flickr recently, a few years ago, did a study where they said, the ones that never get seen, are they any different than the ones that are seen? Their conclusion was, no, they're just lucky. That's a pretty bad statement when you think about it. A lot of potential there. What is happening as far as what's opportunity here? Well, one is that we have a lot more data than ever, exponentially growing. The last 2 years, there was more data generated than the previous all of time, and that's continuing and accelerating. Also, we have Moore's Law. We have more computational power than ever. I remember even 13, 14 years ago, people were saying that, well, CPUs are capped out. We can only do so many cores. And then NVIDIA came along, as the graph shows here. Other thing that happened certainly is the birth of AlexNet. Jeff Hinton's students, Alex and Ilya, particularly Alex, I guess, that's what they named it, AlexNet, I guess. We're doing a classification competition, trying to classify from a large 1.4 million, I believe, images, something like that. Trying to classify into 1,000 categories. Their convolutional neural network, basic architecture shown here, beat the competition by more than 10%, like closer to 15%. So the people before the competition were getting like 72% accuracy. They received something like 85. That is a singularity moment in the industry. Before this point, people, I remember even in the early 90s, were singing the praises of AI. Neural networks came along. People hated them. They became taboo to even use the word because they couldn't explain what was going on inside of them. Now, with this, you see results that are unreplicatable with any other technology. You've seen industries, computer vision, natural language processing now are all dominated by deep learning. All previous machine learning techniques are not used by any of the major players. What type of platform do we work upon? Well, it's typically AWS platform. Last time I'll ring their bell, but they're really good at what they do. We use Docker, we use Kubernetes, so we have microservice architecture, mainly API type services we're offering across literally thousands of pods, huge numbers of services. We collect data voraciously with Kafka, large data lakes. We persist it in all sorts of forms, S3 buckets, Cassandra, Hive, Spark, even SQL, of course. We have data science going on. We use Databricks to connect to Spark clusters and things like that. We use Jupyter. I love Jupyter. I think Jupyter is amazing. We're trying to use it more and more. Of course, we use Python. We use other things. We use R. We use Mathematica even, when it makes sense. We're really big on GitHub. And we have continuous deployment. So if you check something in a GitHub, a PR, and it's approved, it can then percolate automatically right out through dev, QA to prod with proper testing. What frameworks do we use for deep learning? We use TensorFlow, we like Keras. We use Caffe, we use PyTorch. Here's an example of a network here, GoogleNet, but there's so many. We're not bound to one, but TF is our favorite. Certainly we like to use that the most. It's the one that's most widely adopted, clearly, the best support. As we're doing our science, before we get into actual solutions, we have to be able to tell whether it's better or worse than previous results, A/B testing, for lack of a better word. This is one fairly recent test we did. I'm sorry the two graphs are so similar in color, but the lighter color, lighter orange, is the control group. That means it's the old algorithm. Red variation is the new one. This is showing click-through rates as a function of position on page, x-axis, click-through rate, y-axis. High dependency on position on page. And what you see is the two are not different. No benefit. So, short answer, the new algorithm didn't make it. Negative result. Here's a quick example of languages. We support up to 21 languages. This is comparing x-axis as the language in a dictionary of recommended keywords. The y-axis is looking at what actual language is there. We're using machine learning and so forth to identify which language is actually present and sampling all these keywords. You can see only a few languages do well. English is all English, Russian is all Russian, but many other languages, including Dutch, is mostly English. And same with many other Portuguese, so forth. So you would expect a good result. They're all in that diagonal. In this case, they're not. So you got further work to do. Part of knowing where you're at so you can improve it. Lastly, a lot of keywords and things depend upon time. So if you're comparing a result from 3 months ago to a result now, what are you comparing? If the results vary a lot by time, in this case the word pool, swimming pool, of course this is North America, not Australia where it's 6 months difference. You have to know how to handle that and normalize your data correctly. What type of products do we work on? This is one, safe search. So it's becoming an important topic, which is maybe you don't want to show guns, maybe you don't want to show violence in your results, maybe you don't want to show nudity, maybe you don't want to show marijuana for some reason, maybe you don't want to show drugs. You have to define what that is. Traditionally, what's been done in these cases is you use tags contributed by contributors, like we do. The problem is they're not very accurate. If you look at things like Mary Jane here, you might get 30-40% accuracy. If you're lucky looking at tags, might. If you create a binary classifier, trained image, looking at the actual images, do it correctly, you can get human accuracy. You can get 95% accuracy if you know what you're doing. You can also tweak it for your definition of what it is. Clearly nudity in California is not the same definition of nudity in Dubai. So depending upon where you are, you create like a spec, and you say this is what it is, this is what it's not. Then you train it correctly, but then after that, it's all computer, all deep learning, taking care of it. The main area we spend a lot of time on, though, is here. You type a keyword here, Mount Baker. When you've skied in the Northwest, you might have heard of this place, particularly snowboarders. A couple of pictures of it there, particularly the one I'm pointing at right now. Oh, you can't see it right there. Yeah. So this is based on keywords. So you type the keyword, this says, looking through the tags, that this is what we see that are the best choices, most popular choices. Now let's say I really like number 2 in the first row, and I want to see more of the same. So you click on right here, similar image, and you go to this. Well, all these images are done with deep learning. These are a computer algorithm. It's taken each of these images, it's created an image vector, fixed length. It then compares them, and it decides which ones are closest, and that's what you're seeing here. Now, obviously, there's lots of ways you could do that. You could do that where you want very similar imagery, you want identical pictures. Other cases, you might want to take into account that people bought or downloaded the image that they like when they also downloaded other images at the same search. Many ways you could look at it, but this is a very different result. This is not tags at all. This is all deep learning. A lot of the algorithms we use are based upon that core principle, similar image search. We can then take that algorithm and build upon it. Let's say that we want to calculate tags for a new image in a different way, different than I showed you a minute ago, different than the tags that are on our site right now. We could take a given image, and we could say what images are similar, like we just did a minute ago. Then we could look at what keywords they showed up on, those images, and how they performed on those pages. That gives you a real idea about performance as to how well they performed in actual user situations, consumer situations. The problem that you have is that you're not sure how to normalize the data. Because as we showed earlier, blue curve below, that your click-through rate depends upon where you're at on the page, where you're displayed. We can normalize the data, as we're doing here, and produce an inverse probability of click-through type number, the orange graph, then allows you to compare position 1 with position 23 with position 44 results, and they're all comparable. Now you can make correct decisions. If you do that, you can get results like this. Notice that these results are not unigrams. They're almost no unigrams. They're more like what humans type and think. They're not perfect. Any of these results can be imperfect, but they're a lot more perfect than we saw a minute ago. Look at the one here in the middle, jumping child isolated, kids isolated on white, little child dancing, so forth. This one here, cool girl art, woman with backpack, disco dress. I'm not sure if that's perfect. These are all keywords where people, when they saw that image being displayed with that keyword, they clicked on it. It's actually, and it's crossed millions and millions of search events across millions of images. And when you actually look at the results, you see something like this. Now, instead of all unigrams, you have bigrams, 2 keyword phrases, trigrams, even 4 keyword phrases ahead of 1 keyword phrase, the first column, column 1. So we think this is a much better solution. Now, imagine that you want to do something more complicated. You want to find imagery where you want to know, you want to type keywords, you want them to be related to the image, you want them to possess those objects, and you want to tell it where to put the objects in the screen. Positional, spatial dependence. That's a tough problem. Example here, we tell it, and this is a live site, and go to that link and play with it for free, no cost. Here we tell it wine on the left, cheese on the right. You look at the imagery, it's pretty good. You can always find cases where it screws up, but pretty impressive. You're looking at hundreds of millions of images. You can clearly get wrong results. Not impossible. But it's able to do things that very quickly, and this is all done in fractions of a second. Not hours, nothing like that. Okay? You can tell it other things. You can say, oh, I want to have a house behind, upper left, car, bottom right. Does a pretty good job. Now, some of these things aren't houses. This lady in the bottom looks like she's in an airport. This might be in a car dealership showroom, but you get the idea. So how do you do this? What technologies do you use? It's clearly not just a binary classifier. It's clearly not similar image, but it's built on some of those technologies. Well, we use all the following in general terms. So we're using convolutional neural nets. We're using, and I'm going to show how we use these a bit, for both vision and natural language processing keywords. We're looking at where on the image do I care about what's there, and how do I determine that without being told ahead of time where it is? How do I embed this information to bring it all together for one solution? How do I actually solve for the best solution? That's dimensionality reduction, and then, of course, inverted multi-index. So it's a tough problem. It can't be understated how hard it is. When you simply look at just the keyword phrase, you type something like pretty art or whatever, red abstract art, would you know what that picture is? No, you don't. So there's a huge mismatch between what the keywords say and what the image shows. And they're not close to each other. Luckily, we have a lot of images, and so we can learn through example. And we can make up for mistakes with volume. And therefore, we can handle issues that potentially are insurmountable in any small sample. The first fundamental part we look at is, of course, you have one image, and you have a group of images you already know the answer to. You calculate each as through a CNN inference mode that you already trained, and on many millions of images. First one of these we created a few years ago, took a month to generate. Now you can do it quicker. AWS keeps getting better. It's clear it's a significant amount of work. But once you have it learn what it needs to know, now when you use it, inference mode, you say, tell me about this image. It's quick, fraction of a second. So you say, what is the image vector for the bike? What is the image vector for my whole collection? Now let's compare the two. And you're interested in knowing which ones compare the best? Which ones do I think are likely to be the best solutions? Clearly, as you add now keywords to it, Now you're dealing with multimodal embedding. So you have embedding, you create a vector relating the keyword to the imagery, you have vectors for the images themselves, and then you bring them together to tell you which are the closest in both spaces. Referencing this work here, what we're basically doing is we train the vision model first, we train the language model second, and then we look at what is the best approach for that, a MIPS type calculation. So we're looking at which ones are closest to each other. If you look at what these results actually look like, here's an example. I think I can run it here. My one dangerous video to run. So here you have cats. And you see it makes some sense. Now you switch to something like bike. And you see a very different looking result. So these are doing no spatial yet, but they're doing keywords and imagery together. At this point, we don't know where the stuff's located. We just want the stuff. It looks reasonable. Now you do something much longer. You give it a lemur. Now, I couldn't tell you for sure what a lemur was. I think they have a ring tail like a raccoon. So I think some of these are correct, but I'm not a biologist. They're all correct? Even better. I don't know. I'm not a lemur expert. Madagascar, I've seen the movie a few times. I think it's a pretty good movie, actually. This one's interesting because you give it all 5 things. So you're basically saying a family on the beach at sunset, and you see those type of pictures. Still, you're not saying where the sun is, where the people are. You're not specifying that yet. But you're doing a pretty good job. Now you take away the at sunset part, and you see a different set of pictures. So you can see that it does understand with multimodal embedding as to there's these things in the image, but doesn't know where they are. And then it tries to match the best ones, and we do various other aspects to try to get that, but it's doing a pretty fine job. And this is, of course, a business meeting type pictures. So at this point, now it becomes a challenge is where in the picture is the stuff we care about? And so this is the third pillar that we're working on, where we create feature maps, we're pooling the information, we're doing global average pooling, and we're coming up with the best solution. Here's an example of one. You can see in this case it identified mouths, identified chainsaws and people's faces. There's references to it. You can look at the actual math of it. It's not simple, but it's doable. It's not crazy what we're coming up with here. This is a way to get around having to deal with, pixel level knowledge, be able to infer it through other information. There you can see a lemur where it did a pretty good job, or a meerkat. Meerkat, I got it wrong. Different movie. I think that's another one, maybe. Are they the same thing? They look a lot alike. You could be right. Hell, I don't know. I don't know. Here's a bike, mountain bike type episode. Now we found there's some other ways to cast this. Here's saliency casting. We found this to be a bit better. We're still playing with it. Everything I'm showing you here is rather deep research stuff. At this point still, we let people play with it on our site. You can see where the people are. Now you bring all 3 together. So now you're looking at, you determine things that you care about, you apply the vision model, you apply the language model, you bring it all together, and you get the best images. Not something simple to do. Things we noticed and things we learned, like any deep learning exercise, this is not easy. A lot of trial and error, mainly errors. Sort of Thomas Edison stuff. We used a variant of Inception V3 model, but we're not using batch normalization. We found it had issues. We also are using ELUs, exponential linear units, for our nonlinearity that we introduce instead of ReLUs. There's references to that. We're also, as far as the language model goes, we're not using LSTMs because they cause massive overfitting in these cases. We are using a different approach, words with no recurrency, with convolutional neural networks. We're getting good results. So it's like so many things you do in deep learning. You have to try various techniques. Some work, some don't. Sometimes you know why, sometimes you don't know why. And you have to just try until you find the ones that work best. The basic optimization that we're doing is we're looking at the anchor weights, and we're looking at weights between them and the imagery and the keywords associated with those images. We're calculating the best optimization and normalizing it. Something like this, though this is grossly simplified, but we are trying to find the locality of where we think they are located within the image, the things we care about. The wine glass, the car. Still, when we get down to the end, we have a pretty hard problem. If you look at a typical inverted index type calculation that you have to do at the end, it's pretty hideous. So if you do an inverted multi-index, as referenced here, it becomes more of a Cartesian type problem, something much more solvable. Other things that I'm leaving out, but we're happy to discuss, but it's part of what we do, is that even though the things that I portrayed here are of a certain form, that last formula that I showed you, it's still so large, the space that you're searching, that you have a very hard time. So you have to do further simplifications to get it to something, even with all of our great computational power, is we have to do this fairly quickly. Where do these solutions lie on the spectrum of possible solutions? Well, they're not fully supervised. We have tags telling us what's in the image. We don't have tags telling us where it's in the image. If you look at the most extreme case, and there's many examples of this, people actually use like gaming engines, and they'll create imagery within the gaming engine where they know down to the pixel where that human is sitting, where that car is sitting, where that fire hydrant is sitting. That's very different than what we're doing here. Of course, what we like to get to is more unsupervised type use. That's further research. Some people predict that's the future. It probably is. There's far more unsupervised, unlabeled data out there than there is labeled data. But at the end of the day, when you get through with this results, I encourage you to go play with it. It's pretty fun. They look pretty good. And this is an example of helping people find the right image. Doesn't mean everything is perfect. You have to try it out, see what you think. As far as what we're going to be doing next, we're really focused on particularly AR and VR, particularly AR first, augmented reality. So adding things to imagery that may or may not be there, mainly not there. Changing. There was a good article recently Microsoft did where they made people smile better using GAN technology. I think you're going to see a lot of that in imagery. It's going to be a lot more than just making your eyes not red. It's going to be changing a lot of things about the image that you're looking at. You want it to stand in front of a blue screen. You have to remember that most of the images now, in fact, all the things in our archives, are taken with camera. Very few are modified. Pretty much none. In a very short time, you're going to see in the next few years, a huge percentage will be modified. And you won't be able to tell them from the other ones. They'll pass the Turing test, that Turing test. We call them synthetic imagery. And then they'll go all the way to VR, where they produce images that aren't even from a camera at all. They're totally synthetic. And we see a lot of opportunity there, and I think all this relies upon deep learning. I appreciate your time today. Thank you.
So when you find that images are the same, do you store them next to each other?
Right now we don't. The contributors contribute, and you'll see a lot of cases where contributors do a lot of the same shot, slightly varied or not varied at all. We try to detect which ones are the same and remove them on ingestion, but we might fail. That is an area of concern. And just like when you show similar images or when a person searches, they don't want to see the same picture of the dog and boy 100 times. Right. They want to see other dogs and other children or other things. So particularly when you go to similar image, you really want it to branch out. But a normal similar image deep learning algorithm just wants to find exact matches. Most of the benchmark academic type benchmarks are that way. They're saying find the same picture again and again and again. We don't want that. We want other things folded in there like click-through, downloads, how they interact with the media, how it did overall. So there's a lot more information we can fold in there, we can embed to do a better job. And it takes a lot of experimentation. So we're always, one thing that I didn't mention is that all of our testing, 90+% of it, is done in production. We can do rack testing in dev and QA, but it doesn't tell us hardly anything. when you go to production, so you split stream tested, you put 5% of your traffic on that new thing, and then you see what really works. And until you do that, you really don't know, because there's such a wide variety of things that can happen. So the importance of real-time testing or production testing, I call it track testing, like race cars, you don't know until you know. You can only know so much. And so we really put a lot of emphasis on learning in production. So as we go to production, we instrument everything. We're looking at, did it match what we expect? And then when you see new things, is that because there's a bug, something you can't explain, or is it an opportunity? Maybe it's a phenomenon that you can do better at, or you can take advantage of. Any other questions? Yes?
You mentioned that you guys did exception, modified, exponential.
Yeah.
Right?
V3, yeah, modified it, yeah.
Is there a better architecture than exception?
There's tons of architectures, and we can debate within our own team. I mean, I think the really result is put it in production and judge accordingly. And it's like art, and we're dealing with art, right? Imagery. You could argue that which picture is prettiest. I don't know. Which one do you like? So I think, and that's also why that track testing is so important, which is on aggregate, how do you do? So it's like Moneyball, right? You might have stats that aren't that great, but as a team, you're a better team than an individual. And so we really have to look at how we, like with similar images, when we show you 100 images, how in aggregate do we perform? And as we do tweaks, like one of the hardest problems, there's been some really good articles written by YouTube, and we have a lot of work in this area, which is, as you get new imagery, how do you get it on that front page? It's the cold start problem, people refer to it as. It's a bugger, because you don't want to waste real estate, right? You don't want to lose money. But you have to test new images, give them a chance. And so it's a constant research area. But I think that's a great question, and trade-offs.
Like as a follow-up,
Yes.
use any fine-tuning approaches, or do you change
We definitely use transfer learning. Only a fool would not. We definitely do some hyperparameter tuning, absolutely. We do a lot of custom data sets where we tag ourselves. It's all the above is on the table. It's really about the results, right? It's really about what are the results and getting there in a timely manner, which is really the key part. You can't be satisfied with just making it production. You have to see how you do in production and learn. I think the best practitioner of that has been Google search. They release more than 600 changes a year. That's like 2 a day. They don't know what those are going to do, really. They have to monitor it in prod, as they've demonstrated a whole bunch of times over the last, since 1998. So, and since they started doing ads, in like 2004 or something. So it's very challenging, but that's why you do prod testing. Other questions? Yes?
Do you take any steps to proactively promote diversity in the images or people that are?
Absolutely. It's one of the initiatives our CEO is really pushing right now. Just the whole issue of countries. If I'm in Singapore and I ask for coffee shops, do I really want to see pictures from Seattle? Probably not. But that means you have to be able to handle that binary classifier issue that I showed earlier. Can you identify or can you trust your tags? I can tell you right now you cannot. The tags are not reliable. They are bad. So in general, you have to figure out ways to do it with deep learning. But I think it's really a great experiment that's just starting now, which is that issue. And we don't have answers yet. Yes?
So kind of follow up on that question, have you explored using something like Google ground level imaging to cross-reference location with?
We don't use that, but it's a good point. But we don't use Google Maps or any of that. But the users do tell us, and a lot of imagery does come with lat-long type information attached to it. So there's things one can do, and I can't speak a lot further than that. But it's a hard problem that you bring up, and you can't look at old results and say, well, they're clearly better, when you haven't tried the new approach, right? If you try something truly new, if you try injecting, like we do injections, where we'll have a certain percentage of those 100 results, or something totally different algorithm. Maybe they're brand new images in that topic, or maybe a competing topical area. There's also semantic search issues you could use to help with this. So it's a good research area. It's not going to go away. Yes?
You mentioned
Yes.
Do you handle the tagging stuff similarly, so just grab like maybe a frame that weighs 12 frames or something?
I wish I could claim we're perfect at that. We're not, but that's a goal. Yes. We do sample frames, and we do apply these type technologies, but everybody's having problems with that, including Netflix. Everyone who does footage, YouTube, has problems with that. Because what rate, you can sample every second. Typical rep rates you're looking at, even at 30 frames a second, that's 1,800 frames per minute. Pictures you have to look at. That video is 10 minutes long, that's 18,000. That's only at 30. If you go to 60, it's double, 36,000. It quickly becomes an untenable problem. I think there's not many great examples of that currently doing super well. And then there's also the issue of music. How do you sample music? How do you know what's there? How do you know what is a reasonable sample window to look at? We determine on our music which instruments are present, and we record that. We do that with DL, ML type technologies. So it's a good question. It's certainly a hot area. It's a growth area for us. We see it coming up. It's being more and more important. Other questions? Yes.
You mentioned you have more than 1,000 categories. How long are your extended vectors?
Well, as far as for a similar image, or as far, yeah, similar image, they typically are around 2048, those type of numbers. It varies. That's a debate topic too. We've tested all different sizes, factors of 2, 3, 4, up and down around that. You lose fidelity as you go much smaller. You go to 512, you lose quite a bit. As you go higher, it gets diminishing returns. So usually it's 2048 type numbers you're playing with, yeah.
Are those three vectors, or is there more information in each?
It depends which one you're embedding, is what type of embeddings are you using. So you're dealing with the pure image vector, like our image vector service, or whether you're dealing with it, embedding the keyword information into the vector and so forth. And music is different. And so, yeah, it's a continuing research area, and there's lots of debate about which ones are best. It's all about testing in prod. I mean, the reality is, one of the attitudes we have is that, and I lead this group, is that we must be able to test it in prod. It's one of the things we figure out before we do the research. How might we test it? We don't have to have all the answers, but we have to have some idea and some credible belief that we can actually test it in prod. So if you create something and then you can't test it in prod, it never makes it to production. It doesn't stay there, that's for sure. Other questions? Yes. We use a lot of S3, and we use other technologies, Cassandra and things, for storing information about them. We use Akamai a lot, give them a cha-ching. We like Akamai. We use it quite a bit. Makes sense. It's about minimizing the time to get it to you. Other questions? Yes?
Have you guys tried at all some of those AWS application APIs like transcribe recognition, or because you guys are like probably beyond that, you have any thoughts?
Depends upon what we're doing. Like that language confusion matrix that showed up here, that was AWS. The truth, source of truth, the y-axis was that. For most other things like image recognition stuff, we do better, so there's no real point. Also, at the scale we're doing, it just isn't financially viable. And also, even like with binary classifiers, we have to know more than just accuracy. We have to know precision, recall, other information they don't provide on the model. So we can't use it. Also, we have to be able to hand tune them. So one client, make up a company, Facebook may want a certain thing. Another client, IBM, may want a very different thing. How they define nudity for the case they're dealing with. Drugs, whatever. I mean, one of my favorite ones recently is they asked us to ban Taliban. And I'm like, what's that? You have to define it, right? So it's tricky. Just a person in a uniform doesn't make them a terrorist. And in fact, I was in the military for 10 years, the US Air Force, and no, they're not terrorists in general, people, and we have lots of military pictures.
Have you started trying to solve that, or?
Yes. Yep. We have very active work in that area right now. Extremely active. It's a growth area for us, we feel. Other questions? Yes.
Just touching on what you mentioned right at the end about
Yes.
virtual reality coming in. Do you anticipate that it could become like so advanced that photographers, videographers would become obsolete?
Obsolete may not be the right term, but I think there'll be competition. There'll be significant competition. And I'm not sure how that'll turn out. You can already see examples right now where people use, style transfers. You can see one of my picture on LinkedIn where I did a Van Gogh, like deepart.com stuff. You're going to see a lot more of that. And there's been some good examples with that have shown that they can do some pretty interesting things. Particularly like when they look at, they call it deep dreams or something, where they're looking at the learnings that the network has acquired and how it envisions things. There's opportunities here. So whether that's going to make photography go away, I hope not. Because we love photographers. We work with them around the world. 70% of our contributors are not from North America. They're usually from all over other places. Other questions? Yes, last one. Yeah, oh, it's no problem. Yeah. We chose in that case not to use it because when it was used, it caused problems. Yeah, I can't speak a lot more about it. But. Yep.
So how to kind of gauge that it's not being, like the model is not overfitting?
Well, that's always the debate, right? Is that the choices you make in hyperparameter tuning and architecture, do you use dropout rate? What dropout rate do you use? Batch normalization, there's a great talk, I believe, at NIPS in the last year where the guy made fun of it at length for a long time. Became one viral. I think batch normalization usually makes sense, usually. But you can see cases where it doesn't. And so it's case by case, and you have to have some experience with what is a good answer. We have other models that we trust, and so we're comparing and contrasting. That's one of the ways we do sanity checks, source of truth. Because the reality is we can't look at all the weights and biases in the architecture and judge. We can't do that. It's really not viable.
And if not LSTM, what are you guys using for the?
Well, I mentioned in that one reference, I think these will be available, but we're using a word recurrency, non-recurrency, and we're using a CNN, convolutional neural network for that part, for the keyword part. And there's a paper reference in there and stuff too. We like to share that. And I appreciate your time. Any more questions, you can see me over here. Thank you.